So using fully developed flow analysis, we've been able to simplify the Navier-Stokes equations for in radial coordinates for a flow in a pipe down to this very simple, relatively simple looking equation. And we're going to now try to integrate that equation just like we did for flow between two plates to arrive at an actual relationship for V sub z. So we're going to break this into two sides again, like we did before. So on the left-hand side, we'll have dp dz, and on the right-hand side, we have mu d squared vz dr squared plus 1 over r dvz dr. And once again, like we did with flow in a plate, we have already observed that p here is not a function of r. It is only a function of z. So p is a function of z on this side. We could call it f of z if we wanted. And on the right-hand side, we have that equal to a function of the vz function here. Well, we know that vz is only a function of r. It is not a function of z. That, in fact, is the definition of fully developed flow. So we know that it can't be changing in the z direction. So this, just as in the plate situation, this vz is only a function of r. So we'll call it g of r. So we have the situation once again where f of z, a function of z, is equal to a function of r. That is, a function of one variable is equal to a function of an entirely different variable. And those functions can only be equal to each other if they both equal the same constant. This is the same thing as we had with flow between plates. So we'll once again call that constant g because we see that it is in fact dp dz, so that it is the pressure gradient. But it doesn't matter whether it's the pressure gradient or not. The whole point is that these things have to be equal to the same constant or they cannot remain equal because they are functions of different variables. So now we're going to go ahead and just write the equation for velocity in terms of this new constant. So we have mu d squared vz dr squared plus 1 over r dvz dr is equal to g. And now we'll take the mu over to the other side, and we have d squared vz dr squared plus 1 over r dvz dr is equal to g over mu. So that is the equation we're hoping to integrate. Now this equation can be integrated, but it's not as easy as the case where we had flow in a plate. With flow in a plate, we simply had a second derivative over here. It was an integral that I think almost any of you could have figured out how to take. This integral is also fairly simple, but it's not easy to see why initially. This is something that you can stare at for a long time. In fact, when I first saw this integral, that's exactly what I did. I was in graduate school. I had to do this integral. I'd never seen it before. And I stared at it for quite a while, probably I would argue for hours, before I finally saw the trick. But there is a trick to solving this integral. The trick to solving this integral is to recognize the following, that this is equal to this. This integral, this left-hand side can be rewritten as this. So that that left-hand side is equal to this, and I'm going to show that now. It's not obvious, obviously, just looking at it. You'd say, well, they don't really look exactly the same. They certainly have some similarities. But let's go ahead and take this derivative and see what we get. So when you take the derivative, we've got the 1 over r out in front. That's not part of the derivative. We're going to take the r derivative of this. Well, this, of course, is the product rule. So we're going to take the derivative of r times this, and then the derivative of this times r. So the derivative of r times this, well, the derivative of r is just 1. So that's going to be 1 times the derivative times nothing times dv. You don't do anything to the second term, dvz dr. So that's f prime u, f prime g prime f plus g prime. So that's f prime g, and then g prime is the r derivative of the second term. So that would be d squared vz dr squared, and then just times r. So that's the derivative piece. That is, this is your f, this is your g, this is f prime g plus g prime f there, and then you multiply by 1 over r because that's out front here. And when you do that, you get 1 over r dvz dr plus r over r is just 1, d squared vz dr squared. So you get back exactly what we said we needed, but you have a different form for it. So now we can rewrite this equation using this form of that left-hand side. So that's what we're going to do. So the left-hand side is the new form, which is 1 over r d by dr of r dvz dr. And that's equal to g over mu. Now we can multiply both sides by r. So I have d by dr of r dvz dr is equal to g over mu times r. Now I multiply both sides by dr. I have d of something very complicated, dvz dr, equals g over mu times r dr. I can integrate both sides now. The integral of d dvz dr is just r dvz dr. I've said this many times in class. I've said it on video before as well. The integral of d, whatever's in the parentheses, is whatever's in the parentheses. If it's a banana, d banana, integral is banana. D me, integral of d me, integral is just me. So whatever it is, it's just that thing. So it's r dvz dr, no problem. On the right-hand side, of course, I've got a very simple integral. I've got a constant, g over mu, and then I've got r dr. So that's r squared over 2. And then, of course, I have to add a constant integration. All right, so key step here, d of this complicated thing is just that complicated thing. Now I can continue to integrate that. So I've got on the left-hand side, I've got dr dvz dr. So I'm going to take dvz dr. I'm going to multiply divide both sides by r. So I have g over mu. And then I have r squared, that's going to give us regular r, plus c1 over r, because I divided both sides by r. Now I can multiply by r dr again. So I have g over mu r over 2 plus c1 over r times dr. All right, well, I'm going to integrate that as well. And so I have Vz on the left, put my integration sign in here. Vz on the left, because it's just dvz, so the integral is just Vz. And then I've got g over mu r squared, sorry, that's not an r squared over 4 plus c1 ln of r. If you recall your logarithmic integrals, integral of 1 over r is ln of r, and then I have to add a second constant of integration, c2. So my final solution here, g r squared over 4 mu plus c1 ln of r plus c2. And that's what we'll apply our boundary conditions to in order to get our final VZ solution.